Thank you very much for the kind introductions, and it's a pleasure to be here. As Saskia said, I'm on my sabbatical. It's a lovely place to be, so nobody can catch me from Connecticut and say, oh, can you do this? The time difference is fantastic. So what I'm going to talk about today is actually invert the problem a bit. We normally use physics to understand stars. I'm going to tell you how we can use stars, and particularly the sun, to understand physics and learn about physics. Okay. Now, I see a lot of you here. Oops, something is, oh, okay. Sorry, for a minute, I got a shock, things were not working. Now, a lot of you are stellar astrophysicists here, I can see, and those of you who are, you've all heard of Arthur Eddington. And what Arthur Eddington said in his 1926 book was, okay, we can build more and more powerful telescopes and look farther and farther into space. But how can we look inside a star? What appliance, he says, can pierce through the outer layers of a star? We know the appliance is seismology, pulsations, okay? Now, the pulsations of a star are determined by the structure of a star, which in turn is determined by the physics that, determines the structure, the physics and the physical processes. So we want to know if we have enough knowledge of pulsations, can we then use the pulsations to figure out something about physics? So what I'm going to talk about today is give you a few examples where we have learned about the physics of stellar materials using seismology. Now, for stellar astrophysicists, this diagram, it's a standard Hertzsprung-Russell diagram, temperature. On the x-axis, luminosity on the y-axis, so how bright it is. All the colored hashed regions are pulsating stars of different kinds. Now, I am going to concentrate on this little bit here because these stars pulsate the way the sun does, which is tiny, very small amplitude pulsations, but they are randomly excited. So which means if you observe long enough, you will be able to observe most of the modes of pulsation. You can identify them, which is actually the key to learning about physics, okay? Most of this talk is going to be about the sun, how we have used the sun, because for the very simple reason that we have tons of data about the sun, okay? Now, for those of you who are not very familiar with seismology of the sun and stars, our methods are slightly different from what geoseismologists do. So what seismologists on Earth do is there's an earthquake somewhere, and at different places around the Earth, after a time delay, you would see a signature. And the time delay gives you information about the path that the ray paths take. We deal with normal modes. So eigenmodes, in other words, you disturb an object at equilibrium, it'll start oscillating. Those are what we want to do. Ironically, Earth scientists also, these days, they still do use normal modes, but in the beginning, when they started doing seismology, they found this background noise on their seismographs, which now we know is actually the normal modes of the Earth. But that's neither here nor there. So what we are going to deal with are eigenmodes, okay? So let's go to the basics. Since we're going to talk about physics, we need to know how we model stars, okay? The basic assumption we always make, and it holds reasonably well, is that stars are spherical systems. When we make a model, we not only assume sphericity, we also assume spherical symmetry, which in a few slides later, I'm going to break, so don't worry about that. But what we assume is that the internal structure only depends on the radial distance from the core, which basically means we can take a set of 3D fluid dynamics equations and condense them to a set of 1D equations. And 1D is so much easier than 3D. Yeah. So how do we make a star? It's basically a set of conservation equations. Conservation of mass, conservation of momentum, which we generally in this field called hydrostatic equilibrium, okay? Thermal equilibrium. If you produce heat in the star, you have to get rid of it, otherwise the star will do something. We have to talk about transport of energy. Now, I'm going to concentrate, well, the stars we're looking at, it's mainly convection and radiation. Normal stars like the sun, conduction barely plays a role. Now, if you're studying white dwarfs, of course, conduction would be very, very important, okay? And if you're going to study radiation, you need to know radiative opacities. So the radiative opacities are in a slightly different color because it's not something you get a priori from your models. Radiative opacities are calculated by a completely different group of people, and we take their results with grateful thanks and include them in our models, okay? Nuclear reaction rates, again, they're inputs. Now we have to figure out how the abundances of different elements change by various processes. Simplest to think of is in the core of a star, where you're constantly changing hydrogen to helium. Okay. Then, of course, to round it all up, you need the equation of state. The equation of state is a fundamental property of every element that connects pressure, temperature, density, and abundance to each other. Okay. Again, that's an input. Okay. So stars in the beginning used to be modeled as perfect gases, you know, it's hot, everything's ionized. To a large extent, that holds, but not if you're going to do detailed work. So we need the equation of state, and I'll be talking about the equation of state a lot. Now, it's the mass of a star that, to the first order, determines its properties, how long it'll live, how it'll evolve, though you have the metallicity, which is the abundance of elements other than hydrogen and helium, and the helium abundance both play a role. Now, I'm going to talk about the sun. The sun is a one solar mass star, but not all one solar mass models model the sun, because we have a lot more constraints on the sun. We know not only its mass, we know its luminosity independently. We know its radius independently. We know its age independently from radioactive dating of old meteorites, okay? So how do we make sure that our model is actually a model of the sun? Now, it turns out when you look at these 1D models, there are two main free parameters. Neither of them can be observed directly. One is the abundance of helium that the sun was born with, okay? Because the sun wasn't born today, it was born 4.57 billion years ago. And the other is a parameter which actually controls how we treat convection in 1D. It's a completely fudge parameter because we can't treat convection properly in 1D, okay? We call it the mixing length parameter. So you have two constraints, luminosity and radius, two unknowns, why not, the initial helium abundance and the mixing length parameter. Well, two equations and two unknowns, you can solve it. It has to be done iteratively because it's a non-linear set of equations, but we can make a model. Now, a solar model where we make a model with standard physics and don't tune the standard physics, except for why not the helium abundance and alpha, we call that a standard solar model, just like you have the standard model of particle physics. And a standard solar model is extremely useful in testing physics, because if you change, say, a set of, you remove a particular equation of state and substitute it with another, its pulsation properties will change. And we can then determine which one is more correct. So just to give you an idea, this is, think of it as a slice of the sun. The core is right here. That is mainly determined by the nuclear energy generation rates, okay? The outer 30% is the convection zone, which is determined mainly by the equation of state. It's basically isentropic because it's a convection zone. The specific entropy does depend on the metallicity, the hydrogen, and the heavy element abundance. Particularly this interface between the radiative and convective zones, that depends on Z. We know from seismology this demarcation is at 0.713 plus or minus 0.001 solar radii. Very precise. So if you claim your model is good, you'd better be able to reproduce that without tuning. And the radiative zone, of course, has the opacities play a big role. Okay. Oh, by the way, do feel free to interrupt me. I will repeat your question for the people on the Zoom and then answer it. Now, before we go on to how we use seismology to study physics, I want to give you a crash course in helioseismology. And I stress helioseismology here because the sun is actually simpler than some of the other stars that we do seismology of. For one, the sun oscillates in millions of different modes, and we've actually observed millions of different modes, okay? The oscillations are linear and to a very good approximation adiabatic. Adiabaticity does break down towards the surface, but we fudge it and take care of it. All the modes that we've observed thus far on the sun, and I do apologize to some people in some helioseismology folks, but I don't believe the results. So all the modes observed in the sun are either acoustic, meaning sound waves, so we call them P modes, P for pressure, because it's a gradient of pressure, that's the restoring force, or F modes. F modes are simply surface waves. So you see them on the surface of the ocean or the surface of a lake, which have a very, very simple dispersion relation, omega squared equals G times K. So F modes are very good in trying to figure out, do we have the mass and the radius of the sun correctly? Because G and K, okay? Now, each mode is characterized by three numbers. There's the radial order n, which is roughly the number of nodes inside the sun. The degree L, which is the number of nodal planes on the surface. Think of your hydrogen atom wave function, YLMs, that's all we do. And the azimuthal order M, which is the number of nodes along the equator, okay? So M can go from minus L to plus L. Again, just like your hydrogen atom. Now, if the sun were truly spherically symmetric, all modes with the same L and N, no matter what M, would have the same frequency, because to define M, you have to define an equator, but you can't define an equator, a unique equator, if you have something that is spherically symmetric. So in the case of the sun, rotation breaks is the main symmetry breaker, okay? So rotation acts to lift the degeneracy and give rise to rotational splittings. Think of your hydrogen atom again, Stark effect or Zeeman effect, something to lift the degeneracy. And so the difference in frequency between minus M and plus M is related to some known functions, we call them kernels, and the rotation rate of the sun. the interior rotation rate, not just the surface. Now, in the case of the sun, we routinely use L's of up to 250 or even 300. So fitting 600 frequencies per mode, per N, it's a hard task. It increases the random errors. So instead of doing that, what we do is express the frequency of a mode of a given N, L, and M as a central frequency that does not depend on M and an expansion in polynomials. So we usually use the Clebsch-Gordon coefficients. Again, if you're used to quantum mechanics, you know what those functions are. Now, the nice thing about this decomposition is, okay, the central frequency depends only on structure, and that is what I'm going to talk about in the rest of the talk. Odd order coefficients tell you about rotation. Even order coefficients depend on the second order effects of rotation and any other symmetry breaking thing like magnetic fields. So it's a nicely separated problem. Now, different modes penetrate to different regions, different depths of the sun. So I'm showing you a low horizontal wavelength, meaning high degree mode, that only goes to the outer parts of the sun. And I'm showing a low degree mode, which goes very deep inside. And we have modes from L of 0, which go right to the core. And I routinely use modes up to L of 250. Don't quite use 300 because F modes don't tell you about structure. So we can build up a picture of the sun. Okay. What do the data look like? So this is a set of data that I normally use. This is known as an L-mu diagram because the spherical harmonic degree L is on the x-axis and the frequency N is on the y-axis. And these ridges, so this is the F mode, N of 0. This is the first P mode, N of 1, N of 2, N of 3, and so on. Now, the reason these data are so powerful is this. These are 5,000 sigma error bars, okay? And yet we complain we don't have enough data, which is actually true, but that's a different story. So how do we use helioseismic data? Now, normally in astrophysics, we get data. What we do, we make a model, determine the observables from the model, and then look how well the observables match. So in this case, it would be making a solar model, calculating its frequencies, and looking at the frequency differences between the sun and the model. Except that doesn't really work. So if you look at the panel on the left, these are frequency differences, okay? And you see that it's a function of frequency. It can get very large. Remember, the errors are tiny, which is why I haven't even plotted the errors here. And these red dots, which are very low degree modes, they have a slightly different behavior than the higher degree modes, which are these purple dots. Now, this behavior is actually because if you have a mode that only penetrates to a shallow layer in the sun, they're easy to perturb, they're easy to change. The inertia is low. If you have a mode that goes deep inside, to change those frequencies, you have to make much larger changes. The inertia is high. And we can actually calculate the inertia of these modes and then change the figure so that we correct for the effective inertia. And this is the figure on the right now, is the same frequency differences, but corrected for inertia. And you see that, yeah, the main difference is a function of frequency, which becomes larger as frequency gets larger. And unfortunately, this signature has nothing to do with how good or how bad our model is in the interior. Most of this is simply because of the fact that we can't really model the surface of stars very well. We're dealing with, a three-dimensional phenomenon like convection and using mixing length approximation, which even Erika Bamvatense, who actually formulated it, said that, okay, it's just an approximation. If we change some of the surface physics, and only the surface physics, we don't get changes in the interior. So this is the relative sound speed difference between two solar models with slightly different surface physics. And this signature, what we get in the frequency differences, is again just because of the surface. So we call it the surface term. Okay, it's a nuisance term. We could change how we do convection, and we'd get the same, because mixing length approximations come with some various, ways of doing it. Okay, so what do? We have enough data for the sun. So instead of comparing frequencies, we take the solar frequencies and invert them to figure out what the structure looks like. The structure of the interior determines the frequencies. So we take the frequencies and say, okay, what does the structure look like? Now, it's easier said than done, of course, because the relationship between structure and frequencies is this equation. Omega are the frequencies, we observe them. Rho, C are the two variables that we want to find out. Now, P is pressure, but that through hydrostatic equilibrium depends on the density. G is acceleration due to gravity, which again, because that depends on mass, it depends on density. So basically, C and rho are what matter, and psi are the eigenfunctions. Now, we can't observe the eigenfunctions in the interior of the sun. If we did, we wouldn't be talking here. But 1964, S. Chandrasekhar showed that this equation is a nice Hermitian eigenvalue problem, which means we can take a solar model, which is close enough to the sun, and linearize this equation so that we can connect the relative differences of the frequencies between the model and the sun to the relative difference in sound speed and the relative difference in density. And these are connected through known functions. This little bit here is that pesky surface term I was talking about. Okay. Can we do structure inversions? Yes, we can. This is showing the inversion results, the points between two solar models. Okay. I took the frequencies of the two solar models, then figured out the relative difference in sound speed, this one, and density as a function of radius. The solid line is the exact value. So for most of the sun, we do very well. We don't really get the core too well. I mean, very close to the core. I'm talking about radii less than about 0.06 solar radii. So when we want to study the core, we don't do inversions. We take combinations of frequencies. So this is the frequency of a given NL, and we subtract another frequency of a n-1 L plus 2. And this actually has a bit more sensitivity to the core than what we can get from inversions alone. So we call this the small separations or the separation ratios. In astroseismology, this is about the only tool. And what I show in the figure is, I wish I had made this a color figure. So these gray lines are the kernel functions for the nu n and the nu n-1 L plus 2. And the thicker line, and you can see that the kernel functions are mainly sensitive to the surface, not too sensitive to the core. But the solid line, which is basically this function, has much more sensitivity to the core. So at some point, I'll be using this. Now, the first thing we learned from inversions is that our solar models are very good indeed. What these diagrams show on the left is the relative sound speed difference, actually the square of the sound speed difference, I think, between two models. I call them the red and the blue model, and the sun. Look at the axis. Even at the highest difference, it's 0.7% in squared sound speed, so 0.35% in sound speed. Any other field of astrophysics that have said this is zero, we don't care anymore. But as you can see from the error bars, this is a very significant difference. We know why this difference arises. Basically, our models don't have turbulent mixing at the interface of the convection zone and the radiative zone. If we include that, this goes away. The reason for turbulent mixing there is that that is a shear layer in the sun. And we know that from looking at inverting for rotation. And the figure on the right is the relative density difference. So, okay, we can invert. What can we find with inversions? Okay. Physical processes. These are two solar models. Every input, such as the nuclear reaction rate, the opacities, and the equation of state, are the same. The difference is the red model includes the fact that in 4.5 billion years, heavier elements like helium, carbon, etc., can sink down relative to hydrogen. Gravity, right? We just call it diffusion, but it's basically gravitational settling. If you include that, you get the red model. If you don't include that, you get the blue model. So you can see immediately how important fusion is. And we have indirect evidence also, let alone this, is we can actually look at the helium ionization zones in the outer layers of the sun to figure out how much helium there is. If you don't have diffusion, your models will have much more helium than the sun has. So helium has settled down. So this is a simple way of learning physical processes, okay? Now, let's try something more fundamental, a problem which we don't even discuss these days. Yes? I have a question about the previous thing. Why do you still see heat? Oh, that is the lack of turbulence at the base. Yes, we haven't. This doesn't include that. And the reason this doesn't include that is there is no simple way to model that. You need parameters. And free parameters are an anathema to standard solar models. We do not play with free parameters in standard solar models. Yeah. So let's take a look at the solar neutrino problem, which we don't even talk about it anymore. It consumed solar physicists and particle physicists for about 30 years, but completely solved. And what is it? Well, nuclear reactions produce neutrinos. In fact, how do we even know that nuclear reactions are taking place in stars? We've seen neutrinos from the sun. Different neutrinos come from different reactions, and this is basically telling you the neutrino flux. Say this is from the PP reaction. This is, sorry, I can't see this with my glasses. Boron 8 and the HEP reaction. And the different shades of blue are which of the several solar neutrino observatories can actually detect those neutrinos. Pre-2001, this was the solar neutrino problem. The colored bars are the theoretical fluxes. The blue bar, which is almost black on the slides, are the observed ones. And you can see they don't match. For a long time, well, solar models are tricky, right? You have so many inputs. People automatically believe that the solar models are wrong. And an enormous amount of effort was put into correct solar models. However, once we got good helioseismic data, we showed that our standard solar models are actually very good. If in fact we muck about with the core to get the neutrino flux right, this sound speed difference, which I've blown up here, would go somewhere up here to a 10% difference from a fraction of a percent difference. Clearly, it's not our solar models. So what could it be? Well, that's when people started thinking about the fact that if neutrinos are not massless, then electron-type neutrinos can change into mu-type and tau-type neutrinos, mainly mu-type neutrinos. So that's when the Sudbury Neutrino Observatory was built, which can actually detect mu-type neutrinos. And lo and behold, what happens when you can detect mu-type neutrinos? That was the end of the solar neutrino problem. So now the solar neutrinos are used to actually try and figure out what is the mixing ratio of the neutrinos. So what is the efficiency of their changing flavors? But astrophysicists don't care. Yeah. Now, let's talk a bit about the physics of solar interiors. We've talked about inputs like equation of state and nuclear reactions. One of the things you can do is study the equation of state. It's a fundamental property of matter. Do we get the equation of state of stellar material correct? Now, if you read the literature of stellar equations of state, there are two types of equation of state, depending on how you calculate them. One is the so-called chemical picture of the plasma, where atoms and ions are considered, to be basic particles, and that their interaction can be written as a chemical reaction. The next is an equation of state based on the so-called physical picture, where you basically deal with, fundamental particles, electrons and protons and neutrons and nuclei, and their interactions are basically many-body interactions. So what you do is you write down the partition function and then minimize that, okay? Now, of the equations of state based on the chemical picture, if you're old enough, you would recognize the Eggleton, Faulkner, and Flannery equation of state, which was basically Saha equation plus an ad hoc prescription to induce pressure ionization at dense regions, okay? Bound systems are always in the ground state, and heavy elements are considered to be fully ionized in the interior. Now, CEFF is basically EFF, but allows for Coulomb screening, and it actually improves the EFF equation of state considerably, surprisingly considerably, but it's not completely thermodynamically consistent. Meaning, if you look at the Maxwell's relations that different thermodynamic quantities have to follow, they don't do it to the degree they should. Then there is the MHD, which is the Mahalas, Hammer, and Dapin equation of state, which was the first sophisticated equation of state published that you could actually make good solar models with. I know MHD is a bit misleading, the acronym, but these are the names of the authors. Okay. This did include excited states of atoms, and so it actually worked well. It's very good. Then the physical picture, where you actually write down the partition function, the big one is the Opal equation of state, which many of us still use. And also, to some extent, the new one, the so-called free EOS. They're all basically based on the same thing. You have to minimize the free energy, etc. Okay. So how do we test these? I'm not going to talk about free EOS at the moment. I'll come back to that. So if I make stellar models with the 4 different equations of state, standard solar models, compare the frequencies with the sun, this is what I get. Okay, now you can see EFF. You don't have to do an inversion to show, yeah, it doesn't work. The rest, maybe, may not be. And that's why we really need inversions, okay? Now, before I go into this, let me go to Opal and MHD, not at the surface, but in the core. So one of the first results when we had good space-based helioseismic data was this, where Julian Elliott, who was at that time a PhD student at Stanford, showed that the gamma-1 difference between the sun and both an MHD model and an Opal model was non-zero. But MHD and Opal models agreed with each other. So the question was, what happens? So they had to go back to the calculations of the equation of state to figure out what's going on. Turns out that both groups, Opal, which is actually based in Livermore, I think, was that not Livermore, one of the two, and MHD, they assumed the solar core is not hot enough, so we can assume it to be, a perfect, non-relativistic, perfect gas, which means gamma-1 should be 5/3. Except the core of the sun is at 15 million Kelvin, which is hot enough to have a long relativistic tail of electrons. When you have a perfect relativistic gas, gamma-1 is 4/3. And this shows that gamma-1 for the sun is not quite 4/3, but not quite 5/3 either, but something in between. So both the two groups then went back, corrected the equations of state, and the new versions for Opal, both Opal and MHD, were published in 2002. So this was one of the first instances of actually showing that our inputs to stellar models were not correct. What about the outer layers of the star where ionization is happening? That's a bit trickier, but what you can do is use the so-called dimensionless sound speed, because sound speed, remember, we can get from inversions. And given we can also get density from inversions, so we can actually calculate this. Now, if you calculate it for a model, it looks something like this. So it's almost flat in the convection zone. You get this peak here, which is a second helium ionization zone. Okay. And these little dips and peaks are caused by ionization of other heavy elements. Now, if I zoom into this little peak here, and if we look at this figure, the dotted and the dashed line are the EFF equation of state and an equation of state that's even older, the so-called Planck-Larkin partition function. And you can see it doesn't match with that of the sun, which is the solid line here at all. On the other hand, the dimensionless sound speed of a model with the MHD equation of state actually models it, matches it quite well. It's not perfect, because MHD is not perfect. Opal also works to a reasonable amount. In fact, the peak actually depends also on the helium abundance. So you can actually use that to find the helium abundance of the sun by making models of different helium abundances. But you need to have the equation of state reasonably well matched with the sun. Otherwise, you'll get nonsense, which we found when we tried to find the helium abundance using the EFF equation of state. Okay. Another way of testing is look at gamma-1 again, but not in the core, but towards the surface. Look at this. This is gamma-1. Okay. This is the second helium ionization zone. This is the hydrogen and the hydrogen ionization zone and the first helium ionization zone. So if I look at the gamma-1 difference between the sun and models with the different equations of state, EFF, okay, let's forget about it. Look at opal and MHD. They're actually very similar. Opal blue is much better than MHD red in the deeper layers, but closer to the surface, very close to the surface, MHD seems to be better. Turns out the differences rise from how ionized hydrogen is treated. So you can actually understand the difference looking at these gamma 1 differences. What about the free equation of state? Well, we look at one of the ways people have done it. This is work by Alfio Bonanno, is how do you make models, okay, fit only the frequency combinations that are sensitive to the core, and look at whether or not they fulfill the age criterion. What's the age criterion? We know independently that the age of the sun is about 4.6 billion years. So when they did that, with the opal equation of state, they didn't make a standard solar model, mind. A standard solar model, you would make sure that the constraints, luminosity and temperature constraints, are met at the solar age. They let the luminosity, they kept the radius constraint, but not the luminosity constraint and the age constraint, okay? So they said, okay, let's see at what age both luminosity and radius constraints are met. If I have these two equations of state, and this is the probability that density with the free EOS and with the opal EOS. So free EOS seems to be marginally better. Okay. We can also look at nuclear reaction rates. Solar nuclear reaction rates, particularly the PP reactions, you can't really measure them in a lab. For one thing, these are conditions in the sun, 15 million Kelvin, is actually very low energy compared to what you get in a reactor. Say something like CERN or somewhere there. And the other thing is the cross sections are so small that it's very difficult to measure them anyway. So what this shows are the reaction cross sections, actually what's known as the S factor, which is this factor in the cross section at the gamma peak for the important reactions in the sun. So one of Saskia's and mine former students, Earl Bellinger, said, okay, let's look at the frequency combinations and see if we can put constraints on nuclear reaction rates. This had been done in the 90s, but our data were not good enough. Our low degree modes are very good now. We've got a lot of good data. So they made different models and showed how the sound speed and the density would change in the core if they changed the reaction rate. Okay. So the different colors are basically change the reaction rates by a standard deviation or a few standard deviations where we see the uncertainty here. What they found is they can actually constrain how much you can change. So now what they've done is plotted not the sound speed or the density difference, because of course that would require inversions, but those frequency combinations that I talked about. So the gray are the uncertainties, and the different lines for a given equation tell you how much the reaction rate has been changed. So you can see this one is within the errors, but this one definitely is not. And this is the PP reaction. Similarly, there are the other reactions. And you can make a chi-squared surface and show what sort of uncertainties they get using this work. And these uncertainties turn out to be much smaller than the standard uncertainties. Okay. Now, there's other stuff you can do. People have tried to constrain the value of the gravitational constant G. Not with success, because yes, G is not known very well, but G times M sun is known very, very well. And that is what comes in your oscillation equations. But people have tried to figure out what G dot is, that is, how much can G change with time. Then there are also fun stuff like, ooh, do we see axion production in the core of a star? If you're interested in that, I would refer you to a paper by Nuria Vignoles. It's an interesting paper using stellar pulsations, solar pulsations and solar inversions to actually show you that. So I am going to actually, at this moment, make sure we have enough time for questions. So go to some parting thoughts, and I'll field your questions after that in what I've shown you, and maybe even things I haven't shown you. One is the technique of helioseismology allows us to study the sun in exquisite detail. And knowing the structure of the sun and the physics that goes into the models, we can put constraints on the physics, okay? So we've been, for example, as I showed you, being able to show which equation of state might be better than the other. We solved the solar neutrino problem for one, and even put constraints on nuclear reaction rates. And even though I haven't shown you, I just mentioned G, for example, the data have been used to test fundamental physics. So there's a lot of stuff that can be done because the data are so good. Also, because the sun is a very simple star. Some stars are simpler than others. So I am going to stop here and thank you for listening. And I'll be happy to field questions.